Sure. So please go ahead, Surjeet. Right. Thank you very much. I think this microphone's on. Yeah. Okay. Yeah, I'm delighted to be here to actually teach people in person. So it's a pleasure. All right, so I'm going to talk about some new experimental searches for dark matter. Let me, so let's see what this is about. We're all here because we know the dark matter is a new particle as opposed to being a modification of the law of gravity. And pretty much like most other particles in the world, it's not unreasonable to suppose that the dark matter has non-gravitational interactions. If it has non-gravitational interactions, it's very important to try to detect them. How do I get rid of this thing?
No, it stays there. So from it.
Okay. Maybe. Huh? I think it's something in your thing.
No, because this is the screen which is sharing.
Not that, right? It's
Maybe
this is this should be in your computer. Yeah.
Yes, you're right. See if it goes away in a second.
Yeah. Great. Yeah. Okay. It won't be a theoretical physics lecture if there wasn't some technical difficulties. So the real question is, if it has these non-gravitational interactions, how do we detect these interactions? And the challenge, of course, in trying to detect anything about dark matter is that one reason why we call the dark matter dark is because it presumably has very weak effects of the standard model. So you need techniques with very high precision in order to overcome these very weak interactions. This is kind of where the story gets very interesting, which is that in the last 2 decades or so, if you look at this field of precision instrumentation, there have been some very impressive developments. So today, it turns out that one can measure magnetic fields that are smaller than about 10 to the minus 16 Tesla, okay, 0.15 Tesla or so. And that is with these so-called squid and atomic magnetometers. And one can actually measure accelerations that are smaller than 10 to the minus 13 times the accelerator of gravity. And that is through atom and optical interferometers. In fact, this number is a little bit out of date because the LISA Pathfinder experiment proved they could get to 10 to the minus 15 times the acceleration of gravity. And pretty much as that example basically shows, if you ask anyone who actually works in those fields, nobody would say that these numbers are final, right? It's not like they've hit an endpoint or something like that. These fields, in fact, do witness rapid technological advancements. Every couple of years or so, these numbers get better in order to manage so, and people actually have the ability, ways to make them better and better and better. It's very reasonable that these numbers get better by a few orders of magnitude over the next decade or so. Okay. So it's interesting to ask how we can actually use these technologies to detect new physics, and in particular, the physics associated with dark matter, because we're trying to detect very weak effects. So what kinds of particles are interesting to us? And this is kind of where the question really becomes, what do we believe the mass of dark matter actually is? So I'm going to take a very theory blind approach. I just want to know observationally, what do we know about the mass of dark matter? And you may have seen some of these arguments earlier in these sort of a set of lectures, but if you fell asleep during that time, I'll give it to you again. So naively, you might actually say that the mass of dark matter could be anywhere above 10 to the minus 43 GeV, which is the Hubble scale. Anything above that would be a particle in our world. And the highest mass is set by 10 to the 48 GeV, which is that if the mass is larger than 10 to the 48 GeV, dark matter would be what is called a macho. It would bend a lot of light around the galaxy. And the fact that we have been able to see with the galaxy quite nicely, we haven't seen anomalous lensing, puts the limit of 10 to the 48 GeV. So that's the maximum mass a dark matter could have. So in principle, it could be anything above 10 to the minus 43 GeV. There's one other fact we know about dark matter, which is that dark matter actually fits in the galaxy. And the fact that it actually exists in the galaxy puts 2 non-trivial limits on its mass. If it's below, let's say 10 eV or so, it can't quite be a fermion. And that is because of Fermi degeneracy. As the mass of the dark matter goes low, its number density has to go up in order to accommodate the same energy density. If it's below 10 eV or so, you get into sort of Fermi degeneracy, right? You can't put more than 1 fermion in the same mode. If it's a boson, there is no problem. You can keep packing as many bosons as you want. And so there isn't a limit from that. The ultimate limit really comes from the fact that if the dark matter has to fit in a galaxy, its de Broglie wavelength has to be less than the size of the galaxy, in fact, the size of a dwarf galaxy. And that's what gives you the limit of 10 to the minus 22 eV. So that limit is what's called the fuzzy limit, and you probably have had some lectures on that. So that's the lowest limit over. Anything beyond this is what a theorist would make up as their favorite model of dark matter, right? This is observationally all we actually know. And one reasonable guess is that the dark matter may be tied to the weak scale of 100 GeV or so, because the standard model exists over there. So it's not unreasonable to think that perhaps dark matter is tied in some way to the standard model like that. And if that is the case, we have some very nice ways to look for them. It's the WIMP direct detection program that has been around for 30 years or so. And they haven't found the dark matter yet, which is why we have this workshop. And pretty soon, these guys are going to hit what is called the solar neutrino floor, where the scattering of dark matter will be comparable to the rate at which neutrinos from the sun scatter, making it difficult to make progress in that field. So we've got to think about what's the next step in that direction. But more broadly, since we've been looking at WIMPs for a long time, it's interesting to ask, what else can be there in the world, right? What could we actually go and look for in the world? So there is a variety of particles that any theorist will tell you is a dark matter, right? It can be anywhere from 10 to the minus 22 electron volts to 10 to the 48 GeV. That's about 60 orders of magnitude or so. And there are a number of people who believe this is the dark matter because their favorite theory gives that to you. Fantastic. But let's do a simple trial experiment. If tomorrow some experiment somewhere in this vast mass range says the dark matter is here, okay, whatever here is, the next day, in the archive, there will be like 20,000 papers telling you exactly why that model is what this person thought it always had to be, right? So it's not too difficult from the perspective of model building to come up with a model of dark matter that fits anywhere in that vast parameter space, simply because we know very little about it, right? So to me, the question about dark matter is really a question of experimentally, what can we do to make progress in this vast orders of magnitude parameter space instead of putting theory bias into what we think it should be. So let's ask that broad question. I've got 60 orders of magnitude to play. What can I do, right? How can I think about experiments that are able to cover perhaps not all the parameter space, but large swaths of it? How do we systematically think about it? That to me is a scientific question. So today's lectures, I'm going to talk about largely particles like axions, massive vector bosons, things of that sort. We'll also talk a little bit about WIMP experiments. And then in the next lecture, I'll talk about very, very heavy dark matter particles. So how do we make progress over this vast parameter space? So as I said, this is the outline for today's lectures. So in the first part, I'll talk about ultralight dark matter, that is dark matter with a mass between 10 to the minus 22 electron volts to all the way up to 10 to the minus 5 eV or so. How can we think about dark matter in that mass range? What can we do to detect them? Then I'll talk about new ideas to do directional detection of dark matter. This is actually for WIMP dark matter itself. As I said, WIMP dark matter is about to soon hit a problem, which is that the scattering cross-section of WIMPs will become comparable, the rates rather, will become comparable to that of neutrinos from the sun. And the question really is, how do you make progress in that field? And then I'll talk about some newer efforts to talk about something called a magnetic bubble chamber, which is aimed at detecting somewhat heavier, like not too heavy, but dark matter that has a mass between a WIMP and 10 to the minus 5 eV. So that's what that's about. And then we'll conclude for today. So before we talk about dark matter, okay, if I'm interested in just very light bosonic dark matter, how do I think about light bosonic dark matter? Before we talk about dark matter, let's talk about a boson we know and love, which is the photon. Okay, so this is photons coming from a laser beam. All right, and I can think of these bosons as these photons as individual particles coming out of this laser beam. That's a perfectly valid description. But another equally useful description is that this laser outputs a classical electromagnetic wave. Right? I think of this as a classical electromagnetic wave. It's got some electric field. E is E naught cosine omega t minus omega x, and that is a good way for me to think about the photon. And one way to detect the photon is by detecting the time-varying electromagnetic field associated with it. So this is how we detect radio waves, right? If you have a radio wave coming in, you look for the time-varying electromagnetic field associated with the radio wave that drives some current in an antenna. That's how you detect it. So you're going to keep that thought in mind in trying to detect these very, very light bosonic particles. So how do we think about these light bosons as dark matter? What's the story? There are many of these production mechanisms. I'll just give one simple one just to get the point across. But here's the bottom line, right? Just like how with a photon, there's an associated classical field. For any bosonic field, there's an associated classical field with it. So we would simply say A of t, I guess, means an axion because that's an example of a particle I'm interested in. So we would say if the dark matter is a particle called the axion, there's a classical field associated with it. And so we would simply write that as A of t is A naught cosine mt. Okay. The main difference between the electromagnetic field and a particle like the axion, a massive particle, is that for the electromagnetic field, since the photon has zero mass, its energy and momentum are always tied to each other by Einstein's relationship. While for the case of a relativistic particle like the axion, I can have zero velocity, it can be very cold, right? So if I look at the classical electromagnetic field associated, the classical field associated with the axion, it's just an A naught cosine mt. That's it. I've set the velocity effectively to be zero. So if that is my classical field, what this looks like in the universe is that it's basically got a spatially uniform value, right? It has no dependence on space, which means everywhere in space it's got the same value, and the field is simply oscillating back and forth in time. So that's the picture you want to have in your head. So you want to say in the early universe, when the Almighty created the world, the Almighty just set a constant value for the axion everywhere, right? That's what the Almighty did. And in general, you would say that there is no particular reason why this field amplitude had to be zero, right? So when the field has a non-zero amplitude, there will be an energy density associated with it. And in many of these theories, it's not too difficult to get the energy density right. M squared, A squared can simply be the energy density right now. So that's what the field would look like in one production mechanism in the early universe. There are many other production mechanisms as well. But no matter what the production mechanism, we don't live in the early universe. We live here today. And today, the axion is not going to be spatially homogeneous because it's fallen into the galaxy. Density perturbations grew. That's why you and I are sitting here. So this is a completely random field today. That's how we think about it, right? Like all kinds of stuff has happened to it. Even though it's a completely random field, you can talk about a correlation length for the field. You can basically say if the field has one value here at this point in space, how far do I have to go before the field value changes by order 1, right? Or for any random field, I can think about a correlation function. So if you think about that problem in Fourier space for a second, you basically realize that when the field value changes from 1 to something different, right, that is tied to the momentum of the field, right? Because when I'm changing the value of x, that's tied to momentum, right? So we basically know the correlation length, which is the distance that you need to go before the field changes by order 1, should be inversely proportional to the de Broglie wavelength of the field. And that is, of course, 1 over mv, right? So mass of the field times the velocity. Now, for an experiment, I'm not just interested in the correlation length. I'm interested in what's called the coherence time, which is essentially how long do I have to sit and measure the value of the field before the field value changes completely. Okay. Now, the math here is pretty simple. The correlation length is 1 over mv. So you have to go a distance 1 over mv before the field value changes by order 1. The relative velocity between the Earth and the dark matter is also v. Okay. So the coherence time, which is the time it takes for you to transit a distance 1 over mv, is then 1 over mv squared. That's the basic idea here. Now, this is where things get very interesting. When you have to think about it, these particles, okay, I'll sort of give a list of these particles in the next slide or so. But broadly, these particles, axions, or whatever, they come from very high energy physics. But even though they come from very high energy physics, their mass can be very low. So it's not too difficult to write down models of axions where there's an axion whose mass is a megahertz. Okay, so the axion mass is a megahertz. You make use of the fact that the velocity of dark matter of the galaxy is about 10 to the minus 3. You realize the coherence time is 1 over mv squared, and v is 10 to the minus 3, so it's about 10 to the 6 times 1 over m. So you realize that this coherence time for a megahertz axion is about a second or so. Okay, so that's very interesting from an experimental point of view, because 1 second is a time scale that is useful for an experiment. Right? I can think about measuring something for a second. Right? So it's certainly true that in my online lectures, the student attention span is much shorter than a second. But at least for experimentalists, since they're making actual machines, it's not too difficult to construct, some device that can measure a signal continuously for a second. So even though these particles come from very high energy physics, somehow their frequencies and coherence times are time scales that human beings can access with laboratory scale devices. And that's why it's interesting. So what we're going to do is come up with ways to detect this field. And by detect this field, I basically mean I want to detect the oscillating dark matter field. Much like how I'm going to detect a radio wave by measuring the time-varying electromagnetic field, which drives the current in the circuit, I'm going to think about what are the time-varying effects that could be caused by this oscillating dark matter field, and try to think about devices that can detect this time-varying effect. There's a natural possibility of a resonance, because of the fact that the coherence time, 1 over mv squared, is 1 over v squared times longer than 1 over m, the period. Okay, and v is about 10 to the minus 3, which means I can think of this essentially as saying there's a signal in the world which can resonate for 10 to the 6 oscillations before the signal changes dramatically. So I'm going to think about resonant experiments with a quality factor of 10 to the 6. So from the experimental point of view, that's what I have. So let's ask, what kinds of bosons should we be interested in? So let me give you a theory pitch in the beginning. So I'm telling you that these particles can have any mass, 10 to the minus 22 eV to 10 to the minus 5 eV, right? 17 orders of magnitude in mass. So you might think clearly there should be a very large number of models we can write down. But let's be theorists briefly, and before I'll make fun of the theorists in the next slide. So briefly, when you are trying to be a theorist, you might say, look, these particles are such a light mass. And we've spent all these years talking about technical naturalness, radiative corrections, all that stuff. So if this particle is that light, it is not unreasonable to think that the reason why the particle is that light is set by some kind of symmetry, right? So you want some reason why the particle is that light. So you want to think about what kinds of interactions can a particle have so that it's protected by symmetry. And the moment you use the word symmetry, the number of ways in which a particle can interact with you are going to be very restricted. So the symmetry will prevent you from writing down arbitrary terms. So I claim there are only like 7 possible interactions. Okay. So I'm thinking about a boson. Let's think about spin zero particles, scalars. So if you're a spin zero particle, these are axions, particles, very weak couplings. They show up in many UV theories that physicists like, that theorists like. Not clear that the nature likes them, but clearly theorists like those. So if you have a spin zero particle, we can think about how many ways can a spin zero particle interact with the standard model and still have a light mass. There are really only 4 possible interactions you can write down. Okay. So the first is you can couple the field A, okay, that's my scalar here, to electromagnetism through A or F of dual. All right. That's one coupling. And that is a axion-like particle, right? So that's the name that it gets. I can also couple the gluons in a similar way, A or F GG dual. All right. So if a particle couples like that guy gets a name. Okay, he's called DQCD axion. All right. That's because of the fact that when you have a coupling like this, QCD will give a mass to this particle, and this particle can automatically solve the strong CD problem. So that's what distinguishes the QCD axion from a regular axion, is that this has to have a coupling to QCD. You can also write down other general interactions where you can write down a d mu A or F, n bar, gamma mu, gamma phi n. So the n's are some standard model fermions, nucleons, electrons, whatever they are. And that's also a symmetry protected interaction. And much like how this is a coupling that any axion-like particle can have, in general, this interaction will also exist for any axion-like particle. The last one is a way for us to technically naturally couple the Higgs boson itself to this coupling G phi Higgs squared, and that goes with the name the Higgs portal or whatever. It's also used in these axion models. Yes, sir.
Might be a naive question, but why do you have a derivative coupling for this general axiom?
Because I want this to basically be a protected interaction. So I don't want it to give a mass, right? So anytime I have a, good question. So all of these interactions, okay. So this one I've explicitly written out the derivative. These ones also, if you integrate by parts, what you're going to find is that naively these are all, in fact, for this one and for this one, they're actually derivative interactions as well. That is the reason why so the main point is, right, how can a boson interact with a standard model and not get a mass? If the boson interacts with what's called a shift symmetry, then you notice that the shift symmetry will always protect you from getting a mass. So that's why you have derivative interaction, because the derivative interaction automatically guarantees that you have a shift symmetry.
Excellent, thank you.
So this coupling is a little different. This one does not have a shift symmetry directly, but it is simply the fact that this is a dimension 1 coupling. So whatever mass you write for will be proportional to G squared. So that's why there's no quadratic divergence in this particular interaction.
Sorry, one other question.
Yes.
Why are you doing the chirality with this gamma phi pair?
Because if I write an n bar gamma mu n, so that's the other interaction I could have written down.
Yeah.
Notice that if I integrate by parts, that will become d mu n bar gamma mu n. And d mu n bar gamma mu n is actually 0 on shell because it's a conserved current.
I see.
Right? So this is the only operator right now. Right? Okay. How about spin 1? Okay. So if you have a spin 1 particle, and you want it to be naturally light, you require it to have anomaly free standard model interactions, right? So that's how you prevent your particle from getting a mass, right? That's the U1 version of the spin 0 story. So you have 3 more interactions you can write down. Okay. So you can basically say that here F prime is the field strength of the new spin 1 particle. So I have a new spin 1 boson, let's call it B mu, okay, a dark photon or whatever. That'll have a field strength associated with it, just like electromagnetism has F. The F prime is that guy. So standard model particles can have dipole moments under this new interaction, just like how the neutron has a magnetic dipole moment. Right? The neutron can also have a magnetic dipole moment under the new interaction. It's that guy. Okay, so you can write down magnetic and electric dipoles. They're roughly the same. So there are really two operators that you can put there. The other interaction you can talk about is the kinetic mixing. Okay, there is F prime. So F is the photon, F prime is the new degree of freedom. The last possible interaction is that standard model particles may be directly charged under the new gauge interaction. Just like how electrons and protons are charged under electromagnetism, perhaps under this new gauge interaction, standard model particles directly carry a charge. Okay. Now, if that is the case, and you're not putting in very much new physics beyond the standard model, you want this interaction to be anomaly free. You don't want quantum corrections to change that. The standard model, there's only one other U1 that you can assign. Okay, that's called B minus L. Right? So the electromagnetism is one thing that we know is anomaly free, and that clearly exists. The B minus L is the other possible interaction the standard model could have, which would also be anomaly free. So that's pretty much the unique thing with kinetic right now. So even though there's a wide variety of possible, yes, sir.
Sorry, here's the first, the general axiom.
Yeah, this SF2, yeah, is this new one? Is a U1 gauge field?
Yes. So this is the axiom is electromagnetism.
Why do we include that? I mean, the vacuum is trivial in case of electromagnetism.
The what is trivial?
The vacuum. So you can. So this is just a boundary term.
Yeah, that happens when A is constant. So if it's just a theta FF dual, then you are correct that it's a boundary term. It will go over the integrated by parts. But when A is actually a dynamical field, it's not.
Yeah.
Right, because when you do the derivative will hit the A, and that's not zero.
Yeah, exactly. Okay, yeah.
Sure, no problem.
So I have a microphone. Sorry, Surjeet. So P minus L is by far not the only choice. If you are just allow the ratios of charges to be less than 10, it's about 20 million other. Nobody free.
You mean L mu things of that sort?
Yeah.
Yeah, it's fine. Okay. All right. I'm really just interested in the first generation, but you know, okay. Yes. Okay. So if you actually have, if any of these things are actually the dark matter, what you're going to do is basically substitute the value of the dark matter field in all of these interactions. And you're going to realize the dark matter oscillates at a frequency equal to its mass. And all of this will give rise to time-dependent interactions. Right? So that's all you're going to do. You're going to take each of these operators and plug in these values of the dark matter field. And as it oscillates back and forth, you're going to get a time-dependent effect in your experiment. And what you're going to be looking for is a time-dependent signal between 10 to the minus 7 hertz to about 10 gigahertz, which is the mass range that I talked about. So this is the theory view of why this parameter space is not actually as wide as you might think it is. It is a relatively narrow set of interactions you need to consider. But, you know, technical nationals, who cares about technical nationals, right? We have plenty of examples in the world, the cosmological constant and the Higgs boson, both of which are fine-tuned. The fact they're fine-tuned does not prevent them from existing. So our job as theoretical physicists is to look at what's there in the world, not to sit out there and philosophize. So let's ask this question. If you're a hard-nosed experimentalist, you can be like, your philosophy about natural physics is wrong, right? So that's just true. Maybe some person will come up with technically natural ways to make understand the cosmological constant problem or the hierarchy problem, any of those things. But as an experimentalist, your job is to go and see what's in the world and let the theorists worry about what's natural and what's not. So if that's the case, you might be like, is there a much broader range of parameters? Is there a larger set of things you might want to do? So as long as we restrict ourselves to the first generation of the standard model, which is the one that we can actually do experiments with most easily, it's interesting to think about what you might do in cases where you have other generations. But as far as the first generation is concerned, there is a much smaller number of experimental possibilities for you to even pursue. Okay, so let's ask that question observably, right? So whether you believe in this technical naturalist paradigm or not, if you want to try to detect the dark matter in the laboratory, you have to ask what are the possible classical effects that a classical field can have on particles. So what can a classical field do to photons, electrons, protons, and neutrons, the particles that we have access to in the laboratory? So let's think about that. Okay. So I'm going to say the dark matter is some oscillating dark matter field. That's what it is. And you can think about it a lot like a oscillating electromagnetic field, like a CMB, right? Moving back and forth. So the first thing it can do is that it can drive currents in a circuit. Okay. It can also drive directly electromagnetic fields. So I won't talk about it driving electromagnetic fields directly because that's the ADMX experiment, and you probably heard about it elsewhere. It's not a new idea. Okay. There's one thing that I'll list here, which is a direct production of photons. Okay, that's definitely there. So in terms of the newer effects that people have not conventionally looked for, you can essentially have this particular background classical field. It can drive a current in a circuit. It can cause spins to precess. It can exert forces on standard model objects, and it can change the values of fundamental constants. That's pretty much what a new classical field can do to standard model objects. Now, notice the interesting case here, which is that if I drive a current in a circuit, that small current will create a small magnetic field. So I can imagine putting one of these fancy magnetometers, a squid magnetometer or something, next to that circuit and detect that small current. If I have the spin and the spin rotates, as that spin rotates, the spin has its own magnetic field associated with it. And that rotation will actually cause a tiny change in the magnetization of the sample. That's again something I can measure with a squid magnetometer or precision magnetometer. If I directly exert forces on objects, I will create accelerations on them. And as the object moves back and forth, that acceleration can be measured with an optical or atomic interferometer, the kind of things that we talked about earlier. And finally, if I change the values of fundamental constants, it will eventually manifest itself as an effective acceleration. Because if you think about it, even if the distance between two objects is completely fixed, if I'm using, let's say, a laser to measure the distance between me and the object, if the mass of the electron changed for whatever reason, the ruler that I'm using to measure the distance between me and the thing, which is the fact that laser frequency will change. Yes.
In the case you just mentioned, the constant changing, are they oscillating in time?
Yep.
Okay.
All of these are on oscillating. Okay. So what's going to happen is the fact that if I use a laser beam, let's say, to measure the distance between me and that door there, what do? I basically am sending a frequency from here. It hits the door, it comes back to me. And if the mass of the electron changed in the time that I sent it and received it back, right, the frequency would have changed a little bit. So it would seem like that door is moving away from me, even though it's actually not, right? My ruler has changed. So essentially these same ideas, we'll sort of discuss this later in greater detail, but I want to give you the overall picture. You basically see that using these optical and atomic interferometers, you can also similarly measure a change to fundamental constants. Okay. And these are indeed the wonderful technologies that have been developed in the last 20 years or so that one can really use for this. So we're going to make use of these things to talk about the next set of ideas, how to do this. And what's going to be very important is the fact that we're going to look at a time-dependent effect. Okay, so the dark matter is oscillating at a fixed frequency. The fixed frequency is set not by you or me; it's set by the mass of the dark matter, the fundamental parameter of nature. Okay, and it's very narrow. It has a width of around 10 to the minus 6, which is the 1 over v squared we talked about, centered around the dark matter mass, and that is going to be extremely important in order to beat noise and stuff like this. So the first experiment I'm going to discuss is the cosmic axion spin-precession experiment, or CASPER, and I guess this is now funded and people are building. Okay. So let's talk about how CASPER works. So let's think about a neutron, and let's think about this coupling of general axions. So when you actually have this interaction, d mu a n bar gamma mu gamma 5n, you can look at that particular interaction. You can go through some field theory and write it down in the non-relativistic limit. When you write it down in the non-relativistic limit, what will happen is basically that this particular interaction will look like a velocity dot spin coupling between the axion particle and some nucleus or electron. So what does that look like? This looks a lot like how a magnetic field interacts with a spin, right? So we know what magnetic fields do to spins. They make spins rotate. So in this case, what's going to happen is that if you take your spin and the dark matter is moving through it, because there's a relative velocity between you and the spin will start precessing. I'm going to do back and forth. And you can plug in the numbers, look at what the current limits are on these kinds of things. What you're going to find is that effectively you're trying to look for a magnetic field that's a little bit less than a femtotesla. Okay, that's what you're trying to detect. So that's the effective dark magnetic field. So what I've done here is I've put in the values for the velocity of the dark matter, the amount of energy density of the dark matter locally, et cetera, and I've converted this thing into an effective magnetic field. And essentially, we're going to be thinking about how can we detect an effective magnetic field, a dark magnetic field, if you will, that's order 10 to the minus 16 Tesla. Other kinds of dark matter we talked about, like the dark photon, we talked about vector dark matter, under which standard model may have a dipole moment, right? Just like the neutron has a dipole moment under the photon, the neutron and the proton may also have dipole moments under the new dark age boson. They of course will have the same kind of effect because there's just a dark matter thing going through. Your neutron has a dipole moment, so it will also cause the spin to go back. Let's think about the QCD axion itself. So the QCD axion, let's think about a neutron. What happens is that when you have this coupling A over F GG dual, this is the has the same form if you build up the theta term of QCD, right? So there's a famous theta term of QCD which gives rise to the strong CP problem. The strong CP problem is that if you have a theta term over there, that will give rise to an electric dipole moment of nucleons. That's what we have not observed, and that's why there's a strong CP problem. So this particle axion is the dark matter. This A over F will in fact give rise to a small electric dipole moment of all nucleons, protons and neutrons. Okay, and this dipole moment will be along the nuclear spin because that's the only other vector we have. And it's a very small dipole moment. Okay, it's about 10 to the minus 30, 40 centimeters. It's many orders of magnitude smaller than the current limit on the static dipole moment. But very importantly, it's oscillating in time. So what you can do is if you apply an electric field, this dipole moment will now start processing. So just like how a magnetic dipole will process when you apply a magnetic field, if you have an electric field, if you have an electric dipole and you apply an electric field, the spin will also start processing. Okay, so you take a proton or whatever, a neutron, let's say it has an electric dipole moment. If you apply an electric field, the spin will start processing back and forth. That's what's going on. So the basic idea of Casper is that dark matter can cause spin precession. So if you're somehow able to measure the spin precession, you can detect these particles. That's the idea. How does it work? You take a sample of material and you align all the nuclear spins in one direction. Okay. Turns out this is a lot harder to do experimentally than what a theorist would say, but people can do it. So if you basically align all the spins in one direction, and then you let the dark matter do its thing. So if it's, for example, the axion wind effect, which is this derivative coupling we talked about, or the neutron or proton having a dipole moment under this new dark age boson, as the dark matter flows through this, what's going to happen is that the spin will start processing. Right? In the case of the electric dipole, essentially what we're going to do is apply some electric field on the sample. That could be an internal field. So we're going to use something called a ferroelectric, which is a system where there's an internal electric field in the system. And once again, it's going to do the same thing. Basically, it's going to cause these spins to process. As these spins process, the magnetization of the sample will change. And I'm going to use the squid, okay, this very precise magnetometer to measure this tiny change in the magnetic field. There's a natural possibility of a resonance in the system, which is a statement that I can apply a background magnetic field, which will create what is called the Larmor precession, which is something you've studied in quantum mechanics, okay, mu b or whatever, that's what it's called. So when the Larmor precession frequency of the system is equal to the mass of the axion, which is a time-varying precession that's happening over here, there will be a resonant response to the system. Okay, so that's kind of what we're going to be looking for. Now, of course, we don't know the mass of the axion, right? We're very nice if someone told us what it is. So what we're going to do in practice is basically that we're going to pick one value of the magnetic field. We're going to see if we see a signal. Okay, if there's a large measurable precession of the spins. If we don't find it, we will then keep changing the magnetic field slowly, scanning over many, many values of the magnetic field, hoping to find one place where there's a resonant enhancement, and we can see the signal. So that's basically how it sort of operates. Is that a question? No. So let me just project out a couple of projections about where we think we can go and why we're excited about it. So this is a projection for the general coupling of an axion-like particle. So you kind of see that essentially there are two versions of the experiment, say something that uses xenon or helium-3 or something like that. Essentially, these things have abilities to probe well beyond current limits on these particles, and it's very complementary to the ADMX experiment. So the ADMX experiment looks for axions. They look for axions that are heavier than what we're looking for. We're looking for axions that are much lighter than what they have in mind. For the QCD axion specifically, we're going to use these ferroelectric materials that we talked about. Yes, sir.
Just a simple question. Why the supernova 1987 constraints are independent of the axion mass?
Oh, because of the fact that they produce at high energy. right? So supernova everyday constraints, they come from the fact that I'm going to produce these things on an axion and leave the axion. So these are very, very low mass axions. And thus, there's no limit on that stuff, right? It just sets the temperature of the supernova, basically. So it's for hidden photons that you're probably thinking about where there's a limit on the mass, not for axions. Yeah.
Yeah, I was wondering, why can't you just, keep varying the magnetic field to get better sensitivity at even like higher masses?
Well, basically, the largest magnetic field I can apply in the lab is 10 Tesla. So that gives me the highest frequency I can get.
I see. And then this behavior, why does it follow?
Very good. So there's a very interesting fact about why it goes like this, right? That's what you're asking. This is due to the coherence time of the experiment. So we talked about the fact that I should have mentioned this earlier. Thank you for bringing it up. The coherence time, which is how long I actually have to sit and measure the signal, goes as 1/mv squared. So the lower the mass, the longer the time. And typically, if I'm trying to sit somewhere and measure a change to magnetic field with a squid, or this is what I'm doing here, the more time I have to measure it, the larger the response, the smaller the field I can see. So that's why there is this behavior that goes like that.
And you have no way of like combining, if you measure like in chunks, like just observing for a year, like you have no way of combining the signal to noise ratio for each of these chunks.
So that's kind of what we do, basically, right? So when I say this, essentially, I'm saying that I'm assuming, I think we said 3 years per decade of frequency.
Okay, thanks.
Sure. Very good question. Yeah. So as the gentleman correctly pointed out, if you look at this particular thing, we are very, the place where we're maximally sensitive is essentially lower mass axioms, right? So for example, anywhere where this red curve goes below this purple curve is where we'll be sensitive to the QCD axion. So we're going to be sensitive to QCD axions at 10 to the minus 12 eV or 2 10 to the minus 9 eV, which basically corresponds to Planck scale through gut scale axions. And the sensitivity to lighter mass is precisely for this enhanced coherence time. Yes.
Hi. What's this magnetization noise? Is it like the same thing as the regional flow?
No. The magnetization noise is a statement that if I take a sample of material and I have a bunch of spins, the spins will sort of randomly fluctuate, right?
Yeah.
So that random fluctuation will also look like noise in the sense that so I'm looking for a change to the magnetization of the sample. So the spins are wobbling around. That wobbling around will also look like a signal to me. So that's the intrinsic quantum noise, if you will.
So anything to the bottom right of this triangle, you can probe it with like Casper-like experiments?
Yeah, anything on below this, I can't probe with Casper. So magnetization noise is a fundamental limit. So yeah, if you want some detail, so there are good. So there are a couple of lines here, right? So this red line is what we would call as a magnetometer limit, which is the limit set by what is the best, smallest magnetic field I can measure with a squid or something like that. The magnetization noise comes from the fact that if I take a sample, my sample itself will have a wobbling magnetic field. Okay, so if I get better magnetometers, I can keep moving this red line until it hits this red dotted line. But to go past the red dotted line, I have to fundamentally do something much more fancier. I'm going to talk about quantum non-demolition, all kinds of fancy things in order to get below the red dotted line.
But this magnetization noise is a random thing.
Yes.
Whereas your signal is like a coherent thing.
Yes.
So if you were to integrate for long enough,
That's right.
like just
Yeah, if you integrate for long enough, you can, but basically then I need to know the mass of the axion, right? Because essentially we're talking about an experiment one would want to do in say 3 years.
Oh, okay.
So, I mean, I'd be very happy if a grad student willing to integrate for 50 years. But, that's just me.
Okay, good. Thank you.
And on the low mass, do you run into detectors for resolution issues, or can you get all the way to -22?
No, so eventually what will happen is the fact that we'll run into like low frequency noise. Okay, so one of the very important things about this entire game is the fact that you want to think about ways in which you want to suppress noise down. And it's a fact about the world that if you're operating at like highish frequencies, noise from human beings and all that kind of stuff can be kind of suppressed. It's kind of naturally smaller. The lower you go, the larger those things get. So what we can say is that in principle, we should be able to go somewhat below, right? I think we can probably go to maybe a hertz or so, but below that, it gets more and more complicated. It's not impossible, but it just requires more thinking on how to do it properly. Thank you. All right, so Casper is now this plot is kind of old, but Casper is in construction. There are two places where it's being built. One is in Boston University, and the other is in Mainz, actually. And all I can say is that stuff's happening, and we're hoping to make progress and cover more and more parameters. So let me now switch to the second part of the things I want to discuss, which is essentially how can we detect small particles, right? So this is the so-called dark matter radio experiment. There's also a funded operation that's happening at SLAC, built by Kent Irwin. So, one sentence slide about what this thing actually is. We say this is a kinetic mixing between dark matter and standard model. So this is a photon. This is the dark photon, F prime. The dark photon gets a mass, and there's this kinetic mixing between the two of them, which is this operator. If you go to this mass basis, essentially what it looks like is that every standard model particle, the electron, proton, all these guys, that carries a charge will now have an epsilon charge as well. Okay, that's how you think about it. So you basically say there is a new photon, it's got the same mass as standard model, but all standard model charged particles get an epsilonic charge as well under this guy. Okay, so let's think about how to detect that. The idea is basically the following: that if this is the dark matter, there's going to be an oscillating dark electric field associated with it. And if this oscillating dark electric field can drive a current behind an electromagnetic shield. That's the idea. So we're going to build a shield, and inside the shield, we're going to stick in an LC oscillator. So if you build a good shield, that will block regular standard model particles. The dark matter electric field, however, will go inside. It will excite this LC oscillator, right? We don't know what the frequency of the dark matter is, so we want to make a tunable LC oscillator. So you're going to sit out there and keep tuning it, and hoping there is one particular frequency where the dark matter is actually there. And then that's a frequency where you hear the dark matter radio. You get a small current in the circuit, and that current is measured with the spool. That's the idea. Okay. And this is where we project things will actually happen. There's a bunch of limits and all that kind of stuff. But really, what excites me about these experiments is basically the fact that you can cover a lot of territory. All the blue shaded regions are regions where you can actually probe it, significantly extending what you were able to do prior to these kinds of ideas. And these guys, this is to show you how serious it is. They have a noise curve. This is not the dark matter. It's just some thermal noise in the system getting amplified. Let's talk about the next part of the topics, which is essentially how do you detect dark matter with acceleration. So dark matter that actually causes an acceleration. How do you detect that? So I'll again bother Jure by saying is the only other anomaly-free standard model current. What is B minus L? Well, I'm going to give it a mass, and I'm going to say there is a kinetic term for it, of course, and standard model particles carry a charge under this B minus L. And the bottom line is basically that under B minus L, unlike electromagnetism, in which protons and electrons are charged and neutrons and neutrinos are neutral, under B minus L, all these guys are charged. Protons, neutrons, electrons, and neutrinos all carry a charge. This has a very important consequence, which is that if you take electrically neutral atoms, they will be charged under B minus L if they carry neutrons. Right? So hydrogen will be neutral under both if it's just regular hydrogen, but deuterium will have a charge because it has a neutron and there's a neutrino attached to it. So if you take neutral matter, electrically neutral matter, if the B minus L really existed, you will now find there's a force between neutral matter. Right? Because of the new charge that's got. And people actually look for these forces. People try to constrain these all the time to so-called Cavendish experiments. And that constrains this coupling G to be less than 10 to the minus 21. We can ask, can we do better? This is the dark matter. Can you do something like this? What can you do? So the idea is very simple. Okay, the idea is just the fact that if the B minus L boson is the dark matter, okay, there's a dark B minus L gauge boson oscillating everywhere. That's a dark electric field. It's a dark E prime field. And your atoms are now charged under that dark E minus L field because your atom has a neutron in it. So basically, the atom will now get a force directly being exerted on it by the oscillating dark matter field around. This force will depend upon the net neutron number because that is the charge of the atom. And what that means is that it violates the equivalence principle, okay, because it cares about the composition of the object. And so what people say is that the dark matter exerts a time-dependent equivalence principle violating force on matter. The reason why I say this is because there are lots of experiments that look for equivalence principle violation. So by thinking about this as a time-dependent equivalence principle violation, it helps us understand what experiments one can use to constrain and search for this kind of stuff. The other particle is the relaxion. And I mean, I don't know, like you can solve the hierarchy problem. So the bottom line about the Relaxion is the fact that it is a light scalar that's coupled with the Higgs. And since the Higgs gives rise to masses to fundamental particles, when the Relaxion is the dark matter, it will also effectively contribute to the mass of fundamental particles, right? So when the dark matter is if the Relaxion is a dark matter and this thing oscillates back and forth, standard model particles will get up a time-dependent mass. That's what's going to happen. Okay. And so if you think about the fact that a standard model particle is getting a time-dependent mass, and you realize that the particle also has a gradient in the galaxy because it's got a velocity, then there will be a gradient to this coupling over here. That, of course, corresponds to a force on the object, right? Because I have a g phi mq q bar or whatever, and that's the energy of the particle. Once the field has a gradient, there is a force on the object. So essentially, you're realizing once again that this kind of particle will exert a force directly on standard model particles. This is also Euler's equivalence principle because this thing couples to the Higgs. It doesn't care about gravity. It's not Euler's equivalence principle. So once again, this will be time-dependent equivalence principle violation. So what can we do to find these kinds of things? Well, there are a couple of ways one can actually do this. One can leverage all the existing equivalence principle violating experiments that people have built to go look for this. So let me give you a couple of examples. So one is the famous torsion balance experiment of Eric Allenberger's group in the University of Washington. And this is what they do, okay? They take titanium and beryllium, two different elements. And what they're looking for is the fact that if there is a new force between the Earth and titanium and beryllium, what will happen is that one of them will twist, right? They won't be exactly balanced. So that will cause a rotation of this object. Under gravity, they both fall equally, but under a new force, they'll fall differently. So they look for a little rotation of this torsion balance due to, let's say, a new force. We don't care about a new force from the Earth. We care about the dark matter directly coming in and exerting a different force on titanium versus beryllium because the force cares about the composition of the object, like the net neutron number, things like that. All right. So what we can therefore do is look for the rotation of this torsion balance coming from the dark matter. The other experiment that's actually going on at Fermilab now is a version of Galileo's experiment. So Galileo is famously supposed to have gone to Pisa and dropped two different objects and proved that both objects fall in the same rate, whatever the composition and stuff like that. So what these guys are going to do is they're going to drop two different clouds of atoms, rubidium-85 and rubidium-87. They're different isotopes of the same element, and they're going to see if they both fall at the same rate. Okay, and they want to measure that very, very accurately with very good accelerometers. So that's what they want to do. So these experiments are already ongoing, and they want to try and detect equivalence principle violation between the Earth and these objects. And we can pretty much use the same data in these experiments to go and actually look for this effect as well. The key difference for the dark matter versus these existing setups is that a major source of systematic noise for these experiments is the unfortunate fact that the Earth is a sphere and not a uniform gravitational field, right? So think about this for a second. Let's say I go to this particular experiment. I'm going to drop rubidium-85 and 87, and I'm going to see if one of them falls faster than the other. Okay. If they both fell in a uniform gravitational field, it doesn't matter where you drop them, right? They'll fall equal. But the Earth is a sphere. So let's say accidentally or systematically, for some reason, you always end up dropping rubidium-85 a little bit above rubidium-87, right? Just because of your atomic traps and stuff like this. If that is the case, rubidium-87 will end up falling faster than rubidium-85. And that is not because you have discovered an equivalence principle violating effect. It's because of the fact that the Earth is a sphere, right? So co-locating these two objects at the same point on the Earth's gravitational field is an incredibly challenging systematic for these guys. If the dark matter is what you're looking for time-dependent effects, right? So you're looking for a time-dependent effect, the systematic completely goes away because let's say you take sort of rubidium-85 and 87, you drop them from different locations. They're going to keep falling. But let's say you're looking for 1 Hertz dark matter. What you expect to see then is that every second or so, 85 will say fall faster than 87. Right? Because it keeps oscillating back and forth. So because it's a time-dependent effect, this particular major systematic completely disappears, or disappears quite a bit for the stuff. It gets more and more problematic the lower in frequency you go, because then you can model with the rest of the world. But at least at the beginning, a lot of things are actually possible. One can also use pulsar timing arrays, gravitational detectors that people have already built. And as you undoubtedly have probably heard of, there's something called nanograv, which is a wonderful experiment looking for gravitational waves. They're looking for low frequency gravitational waves. The idea is that pulsars emit gravitational waves and they're coming towards you. And if there's a gravitational wave that causes a stretching and squeezing of space between you and the pulsar, the arrival times of the light pulses from the pulsar will keep fluctuating. Right? That's what they're trying to do. And that's the idea here. But the same, you can use pretty much the same experiment to look for dark matter as well, because if the dark matter, let's say, exerts a equivalence principle violating force between me and the pulsar and me will wiggle back and forth, right? That will again show up as a thing that you can look for. The second thing is if you actually have particles like the relaxion, and say the relaxion changes the mass of the electron, okay, it changes the mass of the electron, the location on the Earth, where it is. Even though the pulsar is at a fixed distance from us, right? I'm sitting on the Earth and measuring the arrival time of the pulsar with some atomic clock. Okay, and the atomic clock kicks at a frequency set by the mass of the electron. And if the mass of the electron keeps wiggling back and forth, it will look like the pulsar's distance from me is changing. And that is not because the distance actually changes, because my clock is wobbling back and forth. So you can pretty much use these same ideas to find these things. So it's actually possible to cover quite a lot of territory in parameter space with these kinds of ideas. Yes, sir.
So this pulsar timing array, I mean, I guess I'm thinking the distance from you and the pulsar, and how many pulsars you have in your array, kind of determines the mass that you're sensitive to, or is it?
It sort of does, but so essentially the pulsar is so far away, right, that it doesn't really matter. So you're correct. The pulsar happened to be close. I mean, like, given at the sun, let's say, then that will certainly limit your ability to look at lower frequencies, because then there'll be more common mode kind of thing. But these pulsars are so far away that it doesn't actually effectively become a problem.
I see. Very good.
Yes.
I was wondering if, since the pulsars are like we're kiloparsecs away, do you have to worry about the fact that the dark matter distribution is a little bit different here than on Earth?
Very good. So in reality, no, because essentially, as long as you are moving relative to the pulsar, you will still see it. Right. So you're correct that in general, there's a complicated thing about what's happening on that side, but there's no reason for that to exactly map what's going to go on here. It's generally something totally different. It's an order one.
Okay. Okay. Thanks.
So again, the point is there's lots of parameter space you can cover. Right? That's what's exciting about this. All right. So let me switch to the second half of my talk, which is essentially what we're going to do about WIMPs. All right. We're going to hit the neutrino floor pretty soon. How do we make progress beyond the neutrino floor for WIMPs? And what are we going to do about, I've talked about these kinds of things, right? Axions, hidden photons, all these things, classical field dark matter. Those, if you notice, they are actually between 10 to the minus 22 eV to about 10 to the minus 4 eV. Okay. And here's an interesting question. What are we going to do about dark matter in this range? Right? Why can't we use these same ideas that have worked, that seem to work, okay, at these low frequencies to look for dark matter in this region? Okay, what's fundamentally going to block that? And this actually goes back to the issue we discussed earlier, which is business of coherence time, right? So in an experiment, I have to sit there and wait for some time to actually see a response. The dark matter comes in and shakes something. My sensor has to react to that shaking, and that's when I can actually see what's happening. The larger the mass of the dark matter, the shorter the coherence time. It goes as 1 over mv squared. Okay. So if you actually think about dark matter at 100 gigahertz or so, its coherence time is about a microsecond. All right, and that's something one can actually go and do experiments in. And as you go to lower and lower frequencies, that coherence time gets very long, a million years. So you have no problem sitting there as long as your glass lives long enough to actually go and do that measurement. But as you go to higher and higher frequency, this coherence time gets smaller and smaller and smaller, and thus you just don't have enough time to build the response in your signal before the dark matter becomes completely different. So how do we think about detecting dark matter in this range? Because the energy being deposited over here is going to be too small for conventional WIMP experiments. At the same time, the signal is not coherent long enough for us to actually go and acquire. So how do we think about that? So that's the next couple of things I'll discuss. So we're going to talk about direction detection of dark matter with crystal defects. That's with these guys. So here is the issue, right? Neutrinos exist, right? So if you think about neutrinos and WIMP dark matter, they pretty much have the same scattering topology. They're going to come and hit, your nucleus or whatever, and then the neutrino and the dark matter will just leave without scattering again. So all it's going to do is come and hit a nucleus, and the neutrino and the dark matter goes out of the detector without scattering again. This is unlike typical backgrounds like protons or whatever, neutrons will scatter a couple of times, so you're able to veto. Neutrinos and dark matter do exactly the same thing in your detector. And there's the anthropic fact that the sun exists next to us, which is good, and the sun produces neutrinos. And you can go and calculate what that is. And basically what you see is that you're about to hit the solar neutrino floor quite soon for the case of essentially low mass WIMPs. Okay. So how can you make progress beyond that? So one thing we can basically make use of is the fact that the dark matter is isotropic. It's coming from all directions, while we know the direction of the sun. So if you're able to measure the direction of the neutrino or the direction of the dark matter, okay, you're somehow able to infer that, you can basically veto on things that seem to come from the sun. And by vetoing things that come from the sun, you can basically be like, okay, those are neutrinos, or I mean, well, they could be neutrinos or dark matter, but if you veto all the neutrino events, okay, you can look for the things that don't come from the sun, and that would be dark matter. So that's the idea, right? So if you're able to measure the direction of the incoming dark matter particle, which you can try to infer from the direction of the recoil here, right? You basically can put a 50% cut. You can basically say, if say this nucleus recoiled in that direction, up like this, it could not have come from the sun because the sun produces neutrinos in this direction. And so whatever scattering you're going to do is going to go in this lower halfway, right? So if you can measure the direction of this nuclear recoil, you can infer the direction of the incoming particle, or at least get a bound on it. And by putting a cut, you can figure out whether there was a neutrino or potentially dark matter. The challenge in doing this is that if you want to talk about with dark matter, you got to essentially, given that they've measured these incredibly low cross sections already, if you want to be even in the business of detecting dark matter, you need a very large target mass, right? The question becomes, how are you going to get directional detection, okay, at this of this recoil in this very, very large target mass? So what is a signal? What does it even look like? So let's think about a solid. Okay, I need like solid state densities to even be in the business, or liquid. That's fine too. But I'm going to think about solids. So what happens? The dark matter or the neutrino comes in. It hits a nucleus. The nucleus is going to move forward, and as the nucleus moves forward, it will scatter multiple times. As it scatters multiple times, it's going to create a bunch of damage in the crystal. Okay. Now this shouldn't surprise you, because when a WIMP or a dark matter scatters, I deposit about 5 to 10 keV of energy, and 5 to 10 keV energy is very large compared to lattice potentials in the solid, which are like tens of eV, right? So basically, I put in 1,000 times more energy in this one particle than what the lattice potential is. But this guy is going to move forward and do a bunch of damage. It's like taking a bullet and shooting it into a, like a piece of wood or something. As the bullet goes through, there's going to be a telltale track in that bullet that tells you which direction it came, right? And by making use of a bullet analogy, I proved that I'm a US citizen. So it turns out that if you do the simulation and see what actually happens, you will find there's a telltale damage cluster, okay, which is localized to within about 50 nanometers. Okay, so if you take this few keV particle and you smack it into this particular crystal, it'll move forward, create a bunch of damage. The damage all exists within 50 nanometers. So if you're able to take your solid and look at 50 nanometer length scales, you will see there's a pattern that tells you what direction the recoil was actually. Okay, so we can do a simulation, and essentially you're going to find that when these damage trail happens, you end up getting something like order several hundred lattice vacancies. So essentially in that 50 nanometer region, the lattice is completely screwed up. Okay, it's got like 100 to 200 lattice vacancies, interstitials, all kinds of things. And that damage cascade is very well correlated with the direction of the input. The challenge, of course, is that at the nanoscale, this is a very high signal to noise, because I take a very nice crystal, okay, maybe only a few defects per 50 nanometer cube or something like that. I've done this shooting, this sort of dark matter coming and scattering. Locally, my signal to noise is 100, okay, but it's all very, very narrow. So I need a nanoscale sensor to actually go and see what's actually going on. So let me tell you about this interesting technology of nitrogen vacancy centers in diamond. There are other technologies as well, but this one is something that has been well developed, so that's why I'm going to talk about it. So the nitrogen vacancy center in diamond is something that people have measured and developed over the years. And here's the idea: you've got nitrogen, and so you take a carbon lattice, okay, which is diamond, and you put in some nitrogen in the thing, and you create like a little vacancy next to it. So this is just done by bombarding your sample with some electrons. It sort of does a bunch of damage and does this kind of stuff. What does this look like? Okay, so from the theoretical physics point of view of chemistry, I'm told the actual chemistry is wrong here, but from the theoretical physics point of view of chemistry, there's an unpaired electron sitting over there. Okay, so what an unpaired electron will do is the fact that that's sort of sitting over there And what you're able to do is the following, okay? What these guys are able to do with the nitrogen vacancy centers is that they can shine laser light at this particular electron, okay? That's sitting, this unpaired electron sitting in there, and that will absorb and re-emit the light many, many times. As it absorbs and re-emits the light, you can measure that with some lens or something and figure out what's going on. So it turns out that the spectroscopy of this defect, okay, spectroscopy of this electron is extremely sensitive to the local chemistry and physics in that region. Okay, because essentially this guy is being sensitive to all the atomic fields around it. So you're doing spectroscopy of this defect. Okay, so these are sensitive to crystal environments at the 50 nanometer scale. That's why they built these things to do material physics, to see what's going on at the nanoscale of these things. And people have even demonstrated pretty high densities of these nitrogen vacancy centers of like 1 per 30 nanometer cube, okay, in bulk diamond, like millimeter cube, the diamond has been done. And nanoscale measurement has been demonstrated experimentally around the world, and there is active development of these sensors by many groups happening as well. So the question would basically be the following. Okay, so I know that if I take a solid and this scattering happens, there is going to be this nanoscale signal in that solid. Is that something that I can measure with an ND center? Okay, is that possible? Now you may also be asking this question, look, maybe it is the case that the signal actually exists, right? That I do have these wonderful nanoscale sensors. I've created this little bit of damage. And but what is this guy talking about? He's talking about trying to build a dark matter detector with diamond, right? I already told you that you need a large target mass and to do this, like a ton or something like that. So can I even get 1 ton of diamond, right? And even the DOE gave me money for 1 ton of diamond. Maybe I'll go to Nevada, do something else over there. So what kind of diamond do you need? So this is not the diamond that you might choose to give your spouse. Okay, the diamond that you choose to give your spouse is controlled by a cartel, which knows that you are willing to pay as much money as possible for the diamond. So that's why the prices are very high. The kind of diamond we're talking about is something called poly diamond, things of this kind, which are essentially industrial diamonds. So if you look at the material costs, it's more along the line of $30 to $40 million. We've kind of done the rough estimate for it. So it's not cheap, but it's also not insane, right? So, but you don't have to just stick with diamond. It turns out the same kind of phenomenology is also true for many other kinds of defects in other crystals. So if you look at cesium iodide, okay, which is or sodium iodide, sorry, there are things called F centers that exist in those things. There's similar kinds of stuff, and people have been probing them as well. So this phenomenology is fairly broad. We just study diamond because we happen to know the numbers in that case. All right, so let's see what happens. Okay, so dark matter comes in, you create some damage, and you've knocked off a bunch of these atoms from where they're supposed to be sitting. What will that do, right? What that will do is that this damage will basically create strain in the crystal, right? These atoms are not where they are, they've been knocked around, so they're going to create some strain, and the strain will shift the energy of the transition. That's spectroscopy, because some electric field got wiggled around. So you can go and look at some paper from 1928, which is actually what I did. Some dude in 1928 calculated what will happen when you knock an atom off the lattice. And essentially, this Hooke's law, they'll tell you how much the strain is. It drops as 1 over r cubed. You're going to multiply that by order 100 to 300, which is the number of lattice vacancies you've crossed. And then you can basically go and say, given this strain, can I use Hooke's law, whatever, calculate what is the shift to the line. Okay, so this line has some energy, and now I've created a bunch of damage. And I can be like, well, this damage creates some strain. How much does that strain shift the line here? All right. And the natural line width of the ND center is about 1 kilohertz. And if you do the simulation, you basically find that the ND center line shift is about 100 kilohertz. Okay, 100 times larger than the line width. So it's again a huge signal to noise locally. So the challenge really is like finding a needle in a proverbial haystack, because locally the needle is very different from the hay, right? This is more like finding it is very hard. So even a single ND center has sensitivity to the cascade. So how would you think about doing this experiment? And the way the experiment would work in principle is basically that you think about this detector as essentially a segmented detector, where we're going to think about a large area, maybe a meter square or something like an area, the thickness of about 1 millimeter. We're going to stack them up one by one. Okay, and we're going to create this ND center density of 1 per 30 nanometer cube. And we're going to use very conventional WIMP ideas. I'm not going to come up with anything fancy here. So the WIMP guys know very well, okay, it's scintillation, ionization, things of that kind, to focus on interesting events, right? Because I'm looking at the scale of the problem here is I want to look at maybe a dozen events in a year that I think are interesting, and I want to find the direction of them. I don't want to find the direction of every event that happens. So there will be a dozen events, let's say in a year, that are going to be interesting to me. So I only need to understand the directions for those guys. So I'm going to use conventional WIMP ideas, okay, of looking at ionization, radiation, scintillation, things of that kind, to be like, oh, a few events are probably from neutrinos, a few events are probably from dark matter. So I'm going to look at those few events and try to understand what the direction is for those guys. So if there's a few, if there is some event that I think is interesting, I'm going to go look at that particular section. Okay, so I can localize this thing essentially to within a millimeter or so using conventional ideas of scintillation light, stuff like this. And then I'd be like, okay, so somewhere in this millimeter cube of this particular object, something interesting happened. There's some direction I want to measure. So I'm going to pull out that guy and study that very, very carefully. Okay, so you can essentially very quickly get micron scale localization of what's actually happening here by shining light on the stuff. And you can also do sub-micron, essentially nanoscale resolution by applying a strong magnetic field gradient, it turns out. Okay, so that's again been demonstrated experimentally, where you can be like, okay, you sort of think about this problem in stages. You go from the first millimeter cube to the micron, that's relatively easy to do, and then you apply a strong magnetic field gradient, which then shifts the lines appropriately, and you use that to actually figure out what's going on. So I'll rapidly run through this stuff here. Basically, it's possible with even a few events, one can actually get 5 sigma detection. We've now got preliminary funding to see if this thing makes sense. Thanks to the quantum initiative of the DOE. If you mumble the word quantum, this actually is very quantum. All right. So so there's some cash to actually go and check it out. So we're not me, my colleagues, Ron Walsworth specifically, have a program underway to go and demonstrate this. Yes.
I'm wondering, like you make a detect in a crystal like this, need so much energy or no? Like,
so you think what?
the energy you need to like make a detect in the crystal.
Yeah, it's like a few keV.
A few keV.
Yeah. The point is that the few keV is many times larger than the few EV it takes to knock something off the lattice. All right. So let's talk about the last topic. I think it should get me in time. I hate delaying people's dinners, so especially because I have to eat as well. So we're going to talk about the magnetic bubble chamber idea. Okay, and this is basically this frequency band, 10 to the minus 4 eV to about, let's say, 10 to the 2, the Wim scale, right? What about this? And what we said, the big problem was the fact that the conventional energy that is being deposited is too small, right? I can't use the bolometer that people have worked on for many years. Because that, of course, people have made progress. I shouldn't say it's impossible. People have continually kept making progress going all the way to the side, like lower and lower energy. But they probably won't get all the way to milli-eV. That's going to be very difficult. And the coherence time of the signal is too short to do the kinds of fancy things I talked about earlier. So what do we do? Okay. So in my opinion, people have other opinions as well. But one idea is basically that you need some kind of an amplifier, right? I'm going to deposit a small amount of energy, milli-eV, EV, something like this. And I need an amplified response to the system. So if I have a very nice amplifier of the small energy, I should be able to see this tiny energy deposition. The challenge is basically kind of threefold in some sense. To be in the dark matter business, I need to look at a large target mass, right? Because I need a lot of mass for the dark matter to come and scatter. So I need an amplifier that works on a large target mass. The second thing I require is also the fact that the dark matter is only very rare. I'm interested in like a few events in a year or a few events per month, something like this. So I require an amplifier that is very, very stable. Okay, so what this means is that if you look at a typical detector, like a photon multiplier cube, these things have what is called a dark count rate, which is that you apply, so let's think about a bonehead amplifier, right? Let me take some system and apply a gigantic electric field on it. So it's a gigantic electric field on it. Some electron that gets ionized will get rapidly pushed to the top. That's an amplifier, no problem. Why can't we use something like that? Well, the problem is that if you have some material in general, some electron will be locked in some impurity, something like this. So it'll start tunneling out on its own, just quantum mechanically. And then you have a large electric field, that guy will also get pushed to the top, right? So even when nothing is actually going on, even when there's no actual event happening in your detector, there will be stuff happening, and that's called the dark count rate of your detector, right? So what we therefore require is a system that has very good stability. The amplifier by itself, unless energy is deposited into it, it needs to be stable for a very long time. So you need a very stable amplifier. So how do we do something like that? So here is let's say an idea, right? A cartoon for now. So let's think about the following concept. Suppose I take a system and I have all the spins aligned in one direction. Okay. let me apply a magnetic field in the opposite direction. When I apply a magnetic field in the opposite direction, every one of these spins is now in an excited state. Okay, it's got the Zeeman energy, which is the spin coupling G mu B. Suppose the dark matter comes, it scatters, it deposits some energy. As it deposits some energy, let's say it causes these spins to flip, right? So this spin that's pointing up now flips down. As it flips down, right, this spin, remember, used to be metastable. So as it spins, flip down, it will release the stored Zeeman energy in the system. And that Zeeman energy can now go and the nearby spins, because of heating, and also causes the nearby spins to also flip. So you can create what is called a magnetic deflagration or burning of the material. So essentially what you've done is that it's like I take this thing and I deposit a little bit of heat, the spin starts flipping, and the energy released by that flipping goes nearby, causes the spins next to it also flip. So you have essentially done something like this. Okay, the entire system now starts flipping. All right. So that amplifies the deposit energy, because when I deposit a small amount of energy, I now got a gigantic response to the system. So it's a lot like a bubble chamber. Right? Now the thing is, okay, this is a theoretical physicist talking about it. It sounds like some crazy shit, right? Does it really happen? I mean, you know, and how stable is it? Does it really happen? All right. So this brings up the idea of what's called a single molecular magnet or single molecule magnet. What does it take to have this phenomenology actually work? Notice that you cannot do this in a ferromagnet. Okay, if you take a ferromagnet, if you try to do something like this, it won't work because the spin-spin coupling is very strong in a ferromagnet. If you try to flip a single spin of ferromagnet, the spin wants to go back to where it was because the nearby electrons don't want to flip because of it. Okay, so you require weak spin-spin coupling. Okay, the spins can't be locked to each other. At the same time, you need large density, right? So if I try to use a gas of course has weak spin-spin coupling. But what you want is the fact that when one spin flips, the heat has to efficiently get conducted to the nearby guys so that they also flip. So you require a system where you need large density. At the same time, you have to have weak electron-electron coupling, right? So this is why there are people in the world called chemists, all right? So what you need is what is called an organometallic complex. So what's an organometallic complex? I have no idea. I'll tell you this is a cartoon, right? So an organometallic complex is actually a system where there is a large metal complex. That means there's something like 12 magnesium ions or 8 ion guys, whatever, all stuck together. And they're surrounded by some organic material. You know, these are long formulae, acetate, something, something, alcohol, whatever, okay? So what does it really do, right? What this really does is basically it creates weak spin-spin coupling because these spins are now not right next to each other. They're a little bit further away from each other because it's organic material around you. But the organic material has no problem conducting heat. So you've solved both these problems. And that's why it gets its name in the sense that each molecule, okay, you think of this as a metal complex as a molecule, each of these guys acts as an independent magnet, hence the term single molecule magnet. And these are actually recently discovered systems. The chemists discovered them in the late 1990s, early 2000s. There are about several hundred of these that are known, and the chemists have ways to make large samples. Okay, it's not too difficult to make, apparently. You can buy parts from Amazon and do it. In fact, people have bought parts from Amazon and done it. And this particular crazy phenomenon that I just talked about, right, where I deposit a small amount of heat in one part of the system and it causes the entire crystal spins to flip, has been experimentally demonstrated. It's very well studied in manganese acetate complexes, it turns out. And there are also many other things that people have started investigating. So what's the basic physics? And let's see how it makes sense for dark matter. All right. So how does the system work? How is the stability, etc. work? So the system is supposed to be described by effectively, this is even true, by a two-level Hamiltonian. So when there's no background magnetic field, there are two states: spin up, spin down. They're both degenerate. Okay, and turns out that due to the chemistry of the system, there's an energy barrier between them. That is this U effective that's up there. When you turn on a magnetic field, what's going to happen is that one of these states goes up in energy, right? So that's the metastable state. This is the ground state. But you turn on the B field you turn on should not be so big that it goes above the barrier. You just create this barrier like this. Okay. So what happens is that if you place a system in the metastable state, this guy wants to decay, but to decay he has to go through a tunneling barrier. So the lifetime is set by some exponential of the temperature of the sample and this barrier potential, whatever that actually is. Okay. So what you realize is the fact that at low temperature, these states can be very, very long-lived. But then if you increase the temperature a little bit, right? Not like a couple of two, but maybe an order of magnitude, something like this, right? Due to the dark matter heating, localized heating can very rapidly increase the temperature. It can completely remove this exponential barrier, which will then cause the spin to flip very quickly. Okay, so that's exactly what you want. You want something that is stable because at low temperature, it just lives for a long time with the exponential barrier. You put a tiny amount of heat, removes the barrier, the thing flips. So what sets the energy scale? What energies can we actually probe with this stuff? So let's think about how that physics works. So what we're going to say is that I'm going to take my single molecule magnet, this crystal that I created, and I'm going to initially heat a region of size lambda, okay, to some temperature T. Two things can happen. When you take the system and you heat it up, heat can diffuse from that region. And as heat diffuses, it will lower the temperature. That's one possible process. That process will certainly happen. The other thing that can happen is basically that the temperature can cause the spin to relax, right? That's the other thing. The temperature went up, the barrier was high enough, it's going to remove that barrier potential, it's going to cause the thing to flip. So both of these processes are possible. The spin can flip and release energy and increase the temperature. The key point is the following, okay? The heat diffusion timescale depends upon how large of a region you make hot, all right? So think about it. If I heat up a sample, heat will diffuse out in a random walk. Okay, so the if I make a region of size lambda hot, it takes the time it takes for it to move out of that region scales as lambda squared. So empirically, this is the fact that if you're trying to cook small pieces of chicken versus a large amount of turkey, all right, the chicken will cook in a few minutes while turkey takes several hours. Right, this is the problem I have at Thanksgiving, which is I have to wait for a long time for the turkey to cook, and that's because the turkey is about 10 centimeters in size. It takes several hours, while small pieces of chicken will cook in a few minutes. Okay, so this scales as lambda squared. All right, so the size, the larger the region gets hotter, the more time it will take to diffuse. While this relaxation time is independent of lambda, it doesn't care about how large of a region I made hot. It just cares about the barrier potential and the temperature itself. Okay, so what you basically realize is that this process where you want these spin flips to happen, right? That's what you actually want. You want the heat to get deposited. You want the heat to cause the spins to flip instead of going and diffusing out. Right? So you realize that as long as I take some material and I make a large enough region hot, right? This time scale will eventually become longer than this time scale. And when that happens, when this time scale is shorter than this time scale, what's going to happen is that the spins will start flipping. And as they start flipping, they'll release their energy. That energy will go to the nearby guy, cause them to flip as well. Okay? So the deflagration will occur as long as we heat a sufficiently large region to this temperature. So that's basically what sets the detector threshold, right? You basically look at parameters like this tau naught, which is the intrinsic relaxation time of the system, and you go look at this barrier potential. They will basically tell you what is the minimum amount of energy that you need to set the detector off. And then there are just various tables you can go look at that the chemists have created, where they've got the barrier potential and the T naught or whatever, and then you do this calculation based upon the things like the heat conduction of the system, stuff like this, and that will tell you what threshold, what is the smallest amount of heat you need to set this off. You put in the numbers, okay, you can get something like 10 to the minus 2 eV threshold, very low threshold, and it's very stable. As talked about, because in the absence of energy deposition, this guy will be very stable. Okay. So there's one more important thing that this kind of detector would need, which I didn't talk about earlier, which is that not only do you need the ability to have an amplifier in a large target mass, not only do you need that amplifier to be very stable, you also need it to be the case that the reset time of the amplifier is short. So what do I mean by the reset time? We know that a typical dark matter experiment, the events that are happening are not going to be due to dark matter, they're going to be happening due to radioactivity. So anytime a radioactivity thing happens, your detector will go off, right? It will be like, oh, energy happened, these spins will start relaxing. And then, you can use very conventional ideas to be like, that's not a very interesting event for me. But every time that event happens, I have to reset my amplifier to the ground state, right? Because I need to detect the dark matter again. So if it took me a long time to reset the experiment, to reset my detector, so in a sense, my spins flipped, so all the spins are now in the ground state, right? And now I want to run the experiment again, which means the spins need to reflip and become the excited state again. If that took a long time, I would not actually be able to find the dark matter, because every time a background event happens, I'm losing time simply to reset my experiment, right? So I need an amplifier that is stable and has a short reset time. So let's see how to handle that in this particular case. So this is actually a big problem for these bubble chamber guys, by the way. So the people who build bubble chambers, the typical ones, they have to have sort of reset their bubble chamber every time something happens, background event happens, and the lower in threshold they go, the harder it gets for them, which is why they can't quite do it. So let's see how we can get around this problem. We hope to get around this problem, right? So here are some thoughts about how we do this, how we think we can do this. So your typical background that you actually have in your experiment is going to come from high energy MEV radioactivity, right? You don't need anything as fancy as this to tell you something like this is going on. You just use very conventional ideas, right? You basically be like, oh yeah, this guy produced a bunch of charge, a bunch of scintillation or whatever. So I'm going to use those particular standard things to be like, that's a background event. Okay, I don't care that this is some event, it is a background event. All I want is to know that every time I get a background event, I don't want to reset my whole detector. So how do I do that? So a couple of ideas actually. So here's the main point, right? Because I have these fancy squid magnetometers, I don't need the entire meter cube of a crystal or centimeter cube of a crystal to flip for me to know that an event occurred. As long as a small part, as long as enough of a small part of the crystal flips, I will know something has actually happened. So with a squid, I can essentially realize that when like a 10 to 100 micron region of this crystal flips, I know something happened. What I can then do is I can shut off the external magnetic field, because the fuel in the system that actually goes off is the magnetic field. So I can be like, this event happened, let me turn off the B field. If I turn off the B field, that's it. There is no longer, I've removed all the energy from the system. So the entire crystal will no longer last. Right? So it intrinsically shuts off the thing. And then I can be like, oh yeah, the heat diffused away and now turn it back on. That is one way of doing it. A simpler way of doing it, which is probably what we'll end up doing, is the fact that instead of creating one big crystal, we'll create this in powders, right? A big crystal is typically hard to make. So you create a bunch of powders. Each powder's grain, let's say, is about 10 microns in size. That means your event goes off. All of the spins in a grain, which is about 10 microns in size, will flip. But then the heat is not going to go to the next grain, right? So that automatically prevents this entire system from collapsing. So that's a big difference between a solid bubble chamber like what we have and a liquid bubble chamber, which is what people usually make. Because in a liquid, there's no way in which you can shut it off. It just takes over the whole system. So that would be the kind of ideas we have. We haven't built the whole thing, okay? So we don't know how it's going to work. At least in the theory space, that's what's going to happen. But this is some theory curve of what we can do, okay? So if you look at hidden photons, things like that, we can cover a good part of parameter space if the whole thing kind of works. But let me tell you what's actually happening on the ground. We got some cash to do this as well. We here being Rupak Mahapatra at Texas A&M. So we sort of first thing we tried is basically, okay, the chemists have done the experiment where they take a single molecule magnet and they apply heat on one side, and they can actually see that all these spins relax as you turn, but it's a very conventional heater, right? The question is, does this work with radioactivity? It's just sort of particle detector. So here's the experiment that we did, or not me, Rupak did. So we're going to do the following thing. We're going to create a system that's a Hall sensor. This is a magnetic field sensor. It's not as good as a squid. And there's a sample, okay? And the sample is placed next to a radioactive source. So the sample is a single molecule system. And we actually have two samples. I've only drawn one of them there. So we're going to take two of these samples. There's this manganese 12 acetate, the thing that people have studied. And next to one of them, I place a radioactive source. And the other one does not have a radioactive source next to it, right? And what we're going to ask is the following. What happens, right? I'm going to sit out there and I'm going to see try to measure a change in the magnetization. So initially, I polarize my sample. All the spins are in one direction. I know what the magnetic field is. I'm going to wait for some time and see if the magnetic field direction flips. Because the flipping of the magnetic field direction will indicate that all the spins relax. So what we find is basically this is the data, right? The red line is the sample that was placed next to a radioactive source. The blue line is a sample that did not have a radioactive source next to it. And what you see is that in the red line, right, there's a jump in the magnetization, which corresponds to the fact that all the spins there flip. On the blue line, nothing actually happens. So what this shows is the fact that the radioactive particles that were produced by the source went and hit that guy, deposited their heat locally, and caused this thing to flip. Right. So all I can say at this point is that it turns out that manganese 12 acetate is not a particularly good. Yes, sir.
do you lose something by restricting the size of the material? Like if it's happening where like more spins would have flipped than the size of the material, are you losing some sensitivity?
Well, so you lose like essentially in the case of the powder business, you keep losing like micron cube things every now and then. But that still protects most of your volume. Right. So maybe like once a day you want to reset it, depending on what background you have. But that's fine, right? Like once a day you can spend some time resetting it. It's more like minute by minute, there's no reason to do it. You only lose like small bits of your volume.
I mean, like if you take a powder that's like, I don't know, a certain size compared to like twice the size, you're not losing sensitivity or?
Not sensitive to the dark matter.
Oh, okay.
Because the dark matter just cares about scattering the volume, right? Because the key point is that by making it into powders, I've not lost target volume.
Okay.
Right? But it's still the same amount of material. I've only lost the ability for the thing to conduct the heat across it.
Okay, thanks.
So I'm personally excited by the result of MEV because it's the dumbass theory idea that I come up with, and the thing actually works in the real world. As an experimentalist, there's no reason to be excited about it. But we're hoping that we'll play with newer materials, which we know of, which will hopefully give us better lower thresholds. Yes.
How do I interpret the horizontal axis? This guy takes 100 seconds to fit or what?
Yeah. So there is some activity for the source.
Oh.
So basically, like whatever the scale is, like that is how long you think it'll, how often this will produce like some alpha pump.
Oh, okay. Then how long do I take to like reset this guy?
So we didn't try to reset it, right? Because like this is just a proof of concept.
Oh, okay.
Right. So essentially, the idea would be that in the real world, should this thing ever happen, you sort of set this to maybe let's say 100 microns or something like that, and so that just went off, and you won't reset it immediately. You'll just be like, yeah, okay, that went off. I lost some chunk of the material, and maybe once a day I will wait and then reset the whole thing.
Right.
So that'll maybe take several minutes or something like that, but it's not gigantically long. All right. So with that, let me actually conclude. I'm right on time. So my focus the last several years has been the fact that given the enormously poor observational constraints of dark matter and the extraordinary ease with this theorists can write models, the right approach is to actually think about experimental ways in which we can actually probe large parts of dark matter territory. And I'm personally excited in the sense that the experiments that have been proposed in the last decade or so are now able to probe a significant chunk of dark matter parameter space. And there seems to be sort of interesting things to do. So with that, let me end today's lecture. In the next talk, I'll talk about thoughts on how to probe very, very heavy dark matter. So, thank you.